Okay. Okay. And here you are seeing some pictures about the erection. Erection is a highly challenging one because these are all, hundreds of tons weightage. Okay, and blade length and all, it's like, say, I mean, 100 meters. Such a lengthy blades, and then the gearbox and all, huge weight, right? And of course, transformer and generator. The hub is a really big one, and erection is really challenging one, and it needs heavy foundation because the structure is very huge. Okay, and that's what you are watching here, and if everything is given in feet because it is uh, being done in US. Okay, so that's why they are all given in the feet. Otherwise, same kind of procedure is followed everywhere. Right. And some terminologies in the wind turbine generator. And here you find airfoil. It's also called aerofoil. That is a stream-lined air surface designed for air to flow around it, okay, in order to produce low drag and high lift. Okay, so the wind is flowing, okay, around the blade, okay, and it will produce the lift. Of course, there is also drag forces. Actually, we need to have very high lift and very low drag only we should expect. Okay, so angle of attack, and that is the alpha. Here you find the angle of attack, and sorry, the angle between the relative airflow and the closed of the airfoil. And this is the airfoil, it is closed, and this is the relative airflow, and this alpha is called angle of attack. And here aerofoil design, it's a separate research area, designing of blade and designing of profiles, okay, and the curvature, everything. uh, Hello. Okay. Okay. Thank you. Convocation ನೀವು ಆಗಿದೆಯಾ ಡಿಗ್ರಿ?
19
Okay, so this is aerofoil design. It's another research area. Okay, the aerofoil design is very important for the wind turbine. Okay, the blades really, it's very important. So of course the wind is flowing in this direction, and you find this angle of attack already we have seen, and this is the resultant force, and this is the drag, and this is the lift. Okay, and so the lift should be always high and drag should be always lower. Okay, and say, and it's a small nomenclature, and the airflow over the blade develops lift force and causes the blade to rotate. Because of the lift force, and the blade is getting rotated. And the solidity, there's another terminology in the wind turbine generator, that is a ratio of blade area to the swept area. The swept area, it's the entire circle area, and blade area only the 3 blade area. So that ratio is called solidity, and solidity, and area covered by the rotation of the rotor. That is, the solidity is S equal to pi n b divided by pi d. N is the number of blades. Normally it is 3 only, and b is the blade width, and the d is the diameter of the circle described by the blade. Okay, you know the pi value, and you get the answer. Energy, another terminology in wind turbine generator is energy pattern factor, that is EPF, power from speed distribution divided by power from average wind speed. The power derived from the average wind speed in the particular location, and this is the power from speed distribution. Okay, the ratio of power from speed distribution to the power from coverage speed of the turbine blades. And tip speed ratio, is lambda, actually the ratio of the blades outer tip speed to the upstream wind speed. And yeah, that is the ratio between say the upstream wind speed and the blade's outer tip speed. That ratio is called tip speed ratio. That is lambda. And the best limit I already would have derived பண்ணியாச்சா? The best limit, of course, it is 59.3. Okay, out of 100%, you can derive only 59.3. That is the theoretical limit, beyond which you cannot go at any cost. Okay, that's the maximum limit you could achieve. Okay, 59.3. That is called Bett's limit, and that is actually theoretical limit. Okay, practically you will get only 30 to 40%. That is the capacity factor. Okay, and theoretically you can go up to 59.3, beyond which it is just impossible. And the 59.3, that is the Bett's limit, and how we got it, okay, from wind energy generator. So that is the small derivation here. It is extraction of wind energy. That's a Bett's limit. And so we have the two segments here, the left hand side and the right hand side. The center point, we have the blade, and before the blade and after the blade. Okay, and before the wind turbine and after the wind turbine, how the flow takes place. And actually with the Bernoulli's equation, the derivation is arrived. And so we split into two parts, left side and right side. And I mean, in here, what is the pressure and velocity, and what is the pressure and velocity after the rotor? This is called rotor. Before the on the rotor, what is the air pressure and air velocity? That is just before the rotor. And just after the rotor, what is the air velocity? And I mean, you can see the derivation here. And here I want to say we are making some assumptions. That is, the flow of wind is incompressible. Actually, air could be compressible, but then for the easy derivation, and we make assumptions, the flow of wind is incompressible, and hence the air stream diverges and it passes through the turbine, and the mass flow rate of wind is constant. That is upstream and downstream, and at the rotor, the flow of wind, the mass flow rate, it is always constant. So here, yeah, this is upstream. Before the rotor, it is called upstream. After the rotor, it is called downstream. Okay, and this is at the rotor. Okay, so and so that's what we are going to see here. And what is the pressure and velocity in the upstream side? What is the pressure and velocity in the downstream side? Of course, what is the wind velocity and pressure at the rotor itself? Okay, normally the wind flows, okay, through the rotor, through the turbine, okay, and it hits and it comes out. This is I, that is the inlet, and E, it is the exit. Okay, and so I-A, that is upstream, B-E, that is called downstream. So we are equating the upstream and downstream, okay, based on the Bernoulli's theorem. And here, so what is the pressure and velocity in the upstream and downstream? So pressure, okay, towards the rotor, okay, when the wind is flowing, and when it comes to the blade, that is the rotor, so the pressure is kept on increasing till it reaches rotor. Well, that is a pressure, that is PI, that is the inlet pressure here. Okay, and here pressure at the rotor level, it is just going up. And from the rotor, when it is going out, exit, okay, and from this point it decreases. That is P suffix E, pressure at the exit, pressure at the inlet P suffix I. And of course, P suffix I and P suffix E, it is in the same level and it is equal to P, that is constant. Okay, and that is away from the rotor. The pressure that is called inlet pressure, exit pressure, and both equal to, and both are same. And with regard to the velocity, that is a Vi. Initially, the velocity is there, and then towards the rotor, it is down, and further it is down. Okay, at the exit. Okay, and this is called V suffix I, that is velocity at the inlet. V suffix E, that is velocity at the exit. At the center point, at the rotor point, it is about 2/3 of Vi, and here it is 1/3 of Vi, that is V exit velocity. Okay, and this is about 1/3 of Vi, and this is the 2/3 of Vi, and this is the Vi, right? Okay, so with this we are going to do the derivation, and we make assumption, and all notations P equal to atmospheric wind pressure, P suffix I, V suffix I, pressure and velocity of wind on the upstream of the wind turbine, and P suffix E and V suffix E, the pressure and velocity of wind at the downstream wind turbine. V suffix R, velocity of the wind at the blade or at the rotor, and A, that is area of blade or rotor, and M dot, that is mass flow rate of wind, and density of the air, that is rho. These are the notations, right? So now we are applying the Bernoulli's equation in the upstream and the downstream. As I said, upstream is I hyphen A, that is upstream area, B hyphen E, that is the downstream area. Okay. Okay. So we are applying the Bernoulli's equation in the upstream, that is I suffix A, and downstream B suffix E. Okay, and so based on the Bernoulli's theorem, and we are equating both the sides. Okay, and here you know the output, that is pressure P suffix I, that is the inlet pressure, and off rho E, rho Vi square. Okay, and that's a potential energy, which is again equal to P suffix A plus half of rho Va squared, and this is the nothing but it's a kinetic energy is converted into the useful energy here, and this is half rho Vi squared, and this is half rho V suffix A. A is at the rotor. Okay, this is at the rotor. Okay, and that is 2/3 of Vi here, the velocity, and okay, so the equation P suffix I plus half rho Vi squared, from the kinetic energy it is derived, that is equal to P suffix A, that is pressure at the rotor, plus half of rho Va squared, that is half mv squared, that is from kinetic energy, right? And here the P suffix B plus half rho Vb squared, yeah, okay, and that is the upstream and this is the downstream, upstream and downstream, and so yeah, now you have to substitute the values. Okay, applying the Bernoulli's equation. This is equation number 1 and equation number 2. Here, no, we are just substituting, okay, and rearranging. So by doing all these things, you get the solution. From equation 1 and 2, we are equating equation number 1, that is upstream equal to downstream, the properties, and that's why we are equating from equation 1 and 2. We obtain P suffix A minus P suffix B, and that is equal to half rho Vi squared minus Ve square. Okay, and the force on the rotor disc, we know F, that is force is rho A minus rho B into A, that is half rho A Vi squared minus Ve square, and we are also applying the Newton's second law. Here we applied the force equal to P suffix A minus P suffix B into A, and this is rho of rho A Vi squared minus Ve squared, and this is the force on the rotor disc. And here the force is equal to the change of momentum of wind from the Newton's second law. That is the F that is equal to mass into Vi minus V suffix E. That is equal to rho A V suffix R, that is the speed at the rotor, into Vi minus Ve. Okay. And this is the force. We have two equations, Here this is also force. And here also this is force. Okay, that is with the continuity equation. Equating in equation number 3 and 4, both are same, and we are just pulling out the similar thing one side, and V suffix R that is equal to half of Vi plus Ve. The power output of P wind turbine rating rate of doing work, that is m dot, that is the mass flow, and P that is equal to half of rho Vi squared minus V suffix E squared, and that is we have taken half rho A VR into Vi squared minus Vt squared, Vi squared. So this is a simple derivation that from left hand side and right hand side, and you can frequently change it, and at the end it gives the 59.3%, substituting the value of 5 into 6. So here we have the equation number 5, V suffix R. Equation number 6, here also V suffix R. So we are, whatever we have here, we are substituting in the VR. Okay. And then after substituting and rearranging and with the differential equation, and you get V suffix E that is equal to minus V suffix I. Okay, and that is impossible. Okay, and VE equal to 1/3 of VI, that is acceptable. Okay, substitute VE equal to 1/3 of VI in equation number 7, and all this substitution and rearranging and all these things, after that you can get 0.593 P total. Power coefficient C suffix P that is equal to P max divided by P total, or power output from the wind turbine divided by power available in the wind. Okay, so that ratio is 0.593. Yeah, and I skip all these problems. Okay. Performance and failure analysis. இது கொஞ்சம் பண்ணிட்டே இருக்கீங்களா? ஒரு நிமிஷம் நான் வந்துறேன்.
Yes, good afternoon, students.
Good afternoon, sir.
Yes.
Good afternoon.
Okay. So Betz limit derivations are already discussed with you. So note down the notations, and if you have any doubt, you may ask at the end of the session, right? For the calculations and the substitutions. So at the end of the power coefficient CP, that is equal to 0.593. And this one is a small problem. So the data they have to given for a propeller turbine. So the velocity of the wind they have to given us 20 meter per second for one atmospheric pressure, and the turbine diameter they have to given us a 12 meter, and for operating speed of the turbine they have to given us 45 rpm. So now we have to calculate total power density in the wind stream and maximum power density, and third one is the reasonably power density. So as I told the previous slide how to calculate the total power density, I think third class I discussed with you. Formula for calculating of a total power density, that is equal to which is nothing but your kinetic energy, that is half rho A v cube, right? So here velocity of the wind speed they have to given us 20 meter per second, and density. So how to find the density? So here you know the formula for pressure, P is equal to rho RT. So here pressure they have to given us 1 atmospheric pressure. So 1 atmospheric pressure which is nothing but 1.0132 into 10 power 5, right? So from the formula P is equal to rho RT, you are going to find the value of rho. So rho is equal to P by RT. So here P, which is nothing but your atmospheric pressure. So substitute the pressure value, and R, which is nothing but a constant 287, and the temperature difference they have to given what as 20 degree. So right, so the wind velocity, speed of the velocity 20 degrees, so 20 plus 273, so converted into Kelvin. So the density will comes under 1.205 kilogram per meter cube. So substitute this density value in that formula, 1 by 2 rho v cube. So here u cube, which is nothing but your wind speed velocity, that is a v cube. So the velocity of the wind speed they have to given into the problem 20 meter per second. So that is equal to 1 by 2 density value you calculated 1.205 into the velocity value they have to given the problem 20 cube. So the total power density will comes under 4820 watt per meter square. And second thing, we are going to calculate a maximum obtainable power density. So the formula for maximum power density, in the end of the derivation they have to given what P max, maximum power density, they have to given us 8 by 227. So they have to given a maximum power P max, that is equal to 8 by 27 rho A V cube. So by using this formula, you are going to find a maximum power density. So that is equal to 8 by 27 rho V cube, right? So here rho you calculated already, and the velocity they have to given in the problem. So substitute all those values and find out the maximum power density. So here the maximum power density is 2856 watt per meter square, right? And at last, what we are going to calculate is reasonably obtainable power density. So now calculate the what is a reasonable power density. So which is nothing but the 35% of the total power. So here the total power, which is nothing but you calculated into the step 1, the total power density 4820 watt per meter square. So 35% of total power, that is equal to 0.35 into the total power 4820. So substitute these values and find out the reasonable obtained power density, that comes under 1687 watt per meter square, right? And at last find out the total power generator, how much power you are going to generate. P total, that is equal to, which is nothing but this is a reasonable power density value, that is power into P into A. So A, which is nothing but your area, pi by 4 d square. So D, which is nothing but the diameter of the turbine. So the diameter of the turbine they have to given in the problem 12 meter. So 12 meter they have to given into the problem diameter, and the power density, reasonable power density, you have calculated as 1687 watt per meter square, right? So that is equal to P total, that is equal to 1687 into pi by 4 into 12 into 10 power minus 3 converted into meter. So in problem they have to given meter, so converted into mm. So at last, all the substitutions, the total power we are getting as 190.8 kilowatt, right? So this is what we find in this problem, right? So you just note down all the formulas for the calculations. Uh, First, note down the formula for total power density and maximum power densities and reasonable power density. Just note down the formulas. Now you can do the problem based on this formula. Based by using these formulas, can note down the problem for velocity of wind speed that is equal to uh, which is a 25 meter per second, and same as it is taken into the atmospheric pressure. So as you know what is atmospheric pressure, and the temperature the same 20 degrees Celsius you may take taken down, or whether you can take it as a ambient temperature, whether it is a 26 or 23, 25 something, right? And the turbine diameter you're going to take a 15 meter, and the operating speed of the turbine you're going to take it as a 55 rpm. So the velocity of a wind 20 degrees Celsius is at a 25 meter per second, same 1 atmospheric pressure, and the turbine diameter you're going to take as a 15 meter, and for operating speed of the turbine which is a 55 rpm. Now calculate the same data. Find out the total power density and find out the maximum power density and what is a reasonable power density to be obtained. So calculate these three and tell me the values. And at last you can also find out the total power generated, P total itself you are going to find. So the R value remains constant 287, right? Gas constant, and temperature 20 degree converted into Kelvin. P into 1 atmospheric pressure 1.0132 into 10 power 5. R வந்து gas constant 287 constant அது. Gas constant 287 kilojoule per kilogram Kelvin அது unit. The T into the given problem 20. Okay. 20 degrees or taken as atmospheric ambient temperature 25 or 26. Depending on the problem to 25. Just find out the values and tell me. Yes, and at the end of the sessions, I may ask the answers in person, right? I calculated. Later, I will ask the answer. Now we move on to the next slide. And here the slide shows the additional wind power. And the first scientific basis of wind frame, it was first started in Gujarat and Tamil Nadu in the year of 1986. So the first wind frame was started in Tamil Nadu and Gujarat in the year 1986. And during this period, 1992 to 1996, here seen from the graph, here the your x-axis will shows number of years, and the y-axis will shows wind power capacities. So how much capacity it able to produce in the year of 1994, and how much capacity wind power will be produced in the year of 2000, 2005, 6. That's going on, right? So it's a old data I'm taking as on 31/3/2005. Better you can check it down what is the total installed power capacity as on 31st December 2020, right? I think last class I will discuss about that, so you may note down. And here see the starting year 1986, it initiated in the year 1986, but it was exactly come in the function in the year of 1990 and 1991. It's little bit lower, and in the year of 1996 it can increased gradually for production for the sorry, for generating of the wind power. It may comes around 400 megawatt, and in the year of 2001 to it's gradually increasing up to the year while increasing in the year 2006 and 5 7 8 20 up to the 20, it may increased gradually in the rate for the capacity production by the wind power, for the capacity of generating the energy from the wind power, right? And now see the electricity generation cost. Here your x-axis will show the renewables and non-renewable energies sources, and your y-axis will shows as a cost. So here the cost will start from 0 to the 18 rupees. It's 18 rupees, which is a maximum one. And for a first we are going to take as a coal. For a coal the cost for generation of the electricity is, which is comes under a 2.5, and for a natural gas it comes a 3.9, and for a diesel it's a 10.4. I think it's a old data. The source was taken by the CSTP and NPCIL. So better you can check updated one, right? So for the hydro, by using a water, the cost will comes around to 3.8, and by using a nuclear heavy water and light water, which is a 2.5 and 3.5, and here the wind. So the electricity generation cost for a wind is around 4.2, right? So per kilowatt hour, so per kilowatt hour, which is nothing but 1 unit is equal to 1 kilowatt hour. So for generating of a 1 unit, so the cost for wind is 1 unit is equal to 4.2, right? And for solar thermal, it's come a 15.3, and solar PV it's come under a 17.1. I know you may know what is the difference between the solar thermal and solar PV, right? So in assessment, I may ask the question, what is the difference between a solar thermal and solar PV? I think you are familiar about that. What is the major difference between these two, right? I think this is the old data for generations of electricity per unit cost. So better you can update a later version what it is come, what is the cost for 1 unit for wind or solar thermal, solar PVs or coal, natural gases, all the gas, all the renewables and non-renewable energies, right? And here land requirement hectare per if you are going to generate 1,000 megawatt, right? How many hectare is required for generating 1,000 megawatt? So here your x-axis will show the renewable and non-renewable energy sources, and your y-axis will show the area land required in terms of a hectare. And for a coal, for operating a coal power plant, it takes only a 250 HA only, right? And for a natural gases, which is lower land required and compared with the coal. And for a nuclear, which is equal to the coal, same as it is a 250 HE required for generating of 1,000 megawatt. And for a solar, it comes around a 2,500 megawatt, sorry, 2,500 HE for generating of 1,000 megawatt, right? So we required land required is 2500 HA, and for a wind 3000 HA we required for generating 1000 megawatt. Can anyone say why the wind required a huge why the wind required a huge land when compared with the solars or some other renewable and non-renewable sources? Why? What is the reason?
Because of wind flow, we need large area and bigger blades also
Bigger blade.
to harness that.
Okay. I think what is the feet for a one blade? What is the length?
Around feet, from the slide itself. So,
Yes, a previous slide you may have seen. That's why I'm
yes,
asking.
sir.
Yes. Have you noted down or not? Can you show the slide again? 1 second.
Okay, sir.
Yes. So see the slide. So the dimensions will be given for a blade. How? What is the length in terms of a feet, and what is the hub size in terms of a feet? They have to given. You just note it down. So the blade 131 feet length. The blade 131 feet, right, in terms of feet, and hub which is at 10 feet, right? So as I told, what is a rotor in previous slide? What do you mean by rotor? So last class I told what is rotor.
So the center rotating part, sir, which is coupled to generator,
Yes,
the shaft, sir. Solar.
it is a joining of what?
The
Joining of
hub and the motor.
joining of
The hub and the generator shaft.
hub and generator shaft. Is it right?
Sir, blades and hub.
Yes. So blades and hub are joining together when it is say as a rotor, right? Blade and hub while joining together, so the whole part will be set as a rotor, right? So just note down the blade feet and hub feet, and here the from the ground to the hub, what is the length? It comes around 262 feet. 262 feet from the ground to the hub. It's a distance. It's a 262 feet, and from the ground to the top of the rotor, tip of the rotor. I mean tip of the blade also. So it's 393 feet full height. It is a full height of the wind frame from the ground to top of the tip of the rotor from the ground, which is a 393 feet. So please make down the datas. It's very important while if you are going to design one blade, or if you are going to design an aerofoil, so you just these datas are required. Based on these datas you are going to design a new one, so you just note on these datas, right? Okay, I will move on to the slide. Back to the slide. Yes. Yes, yes. Tell me now. Tell me what is the why the land required is high for wind when compared with some other renewable and non-renewable sources. Yes, yes. Tell me why the land required is high for a wind.
Just for
The
flow of wind,
distance
sir.
between two should be more, sir.
Distance between the two blades should
Two
be more.
windmills, two windmills, sir. பக்கத்துல ரெண்டு windmill இருக்க கூடாது.
Yes. Okay. Yes.
பட்
Yes, that's
அந்த
the
ஏரியாக்கு ஒரு windmillனால கம்மியான எனர்ஜி தான் சார் ப்ரொடியூஸ் பண்ண முடியும்.
yes, exactly. So for example, if you are going to generate 1,000 megawatt, okay, by using a 2 windmills or 1 windmill, whatever it is, okay, it requires 3,000 HA, right? So why? Because the size of the blade, the length of the blade should be higher, and moreover the distance between the two wind frames we should maintain some distance, some more distance between these two wind frames, right? So it requires huge areas when compared with some other renewable energy sources, right? And see the performance analysis factors. So what are the performance analysis will be available? The technical availabilities and the real availabilities and the capacity factors. So technical availability, which is nothing but we are difference between the total emission times and downtime to the due to the grid and the machine failures to the total mission time, right? And just note down the formulas here. What is the technical availability and what is the real availability and what is the capacity factor. So these formulas we are using to solve the problem. By solving the problems, these formulas we are going to take. So you just note down these technical availability formulas and real availabilities and the capacity factor. So here the capacity factor, which is nothing but how much energy generated per year to the turbine rated power into the number of turbines into the number of hours per year. So here the number of hours per year is 8760, and the number of turbines, how many turbines you are going to operate, majorly for a one wind frame, you are going to operate a one turbine, and the turbine rated power. So the turbine rated power they have to given into the problem, and you are going to find only energy generated per year. So the energy generated per year, from the starting of the class, sir will told how to calculate the energy generated per year in terms of a kilowatt hour. I think, you may know how to solve the, sir, how to find the energy generated per year in terms of a kilowatt hour, right? So by for going to calculate a capacity factor, so you should know the value of energy generated per year and what turbine rated power. So these two is only known factors, and the remaining number of turbines and number of hours per year, you may know what it is, right? So you just note down fast. I will move on to the next slide. So based on these three, we are going to solve one simple problem at the end of the session, right? Make it note fast. Yes, here this slide shows per year. So this slide will shows up how performance analysis. So here they are going to take a monthly average wind speed density in the Mupandal wind frame. So I think you are all familiar about that Mupandal wind frame. So how much the total installed capacity they are generating as on 31st December 2020. We are discussing these things in previous class. So 1,500 megawatt energy they are capacity of energy they are generating in a Mupandal wind frame, which is located into the Kanyakumari district, right? So here I'm going here they are going to take Mupandal wind frame monthly average wind power density. So here your x-axis will show the number of years months, and the y-axis will show the power density in terms of a watt per square meter, right? So here from the April, it comes around 175.3 watt per square meter, and in the month of May, it's increased enormously. Why? Because it's a summer season. May month is a summer seasons, right? And moreover, here it comes around 868 watt per square meters. So the average wind speed will be the higher for the month of May, and it goes gradually. And here at the end of the December, November, it down decreasing, so it down, and gradually it may increase, and those it shows varies from the year, sorry, month to month. The average wind speed density may be varied. So it shows the variations in the wind power densities due to the seasonal variations. So due to the seasonal variations, it may be varied, and the maximum wind power density which is occur in the year of, sorry, in the month of June. So it comes around to 723.3 watt per meter square in the month of June. And the average wind power densities in the wind frame is here we are going to take an average. So the average while coming is what 361 watt per meter square, right? And for a high wind power density was recorded from the month of April to September. So here from the April to September, so it is only above the 500 apart from the April. From the May, June, July, August and September, so the maximum average wind power density while coming above 500 watt per square meters, right? So it is, which is the highest wind power density will occur in the month of May to September, right? So after October to March, so it comes lower wind power density was recorded from the month of October to and March and April, right? So it comes under below 200 watt per square meters. So it takes it maybe depends upon the due to the seasonal variation. So due to the seasonal variation, so the power density, average wind power densities may be varied, right? And this is a power generations of the wind frame, same in the Mupandal wind frame. uh, so in the year of 2000 here, it can generate this much amount of a kilo generation of power. And in the year of 2001, 2, 3, so it is old data. The data will be available up to the 2004, and now it is updated one. So as I told just now, in the year of 2020 31st December, the Mopandal wind frame will able to produce a maximum power generation is 1500 megawatt as on 31st December. So can update yeah, update in the year 2020, 19, 18 and from the 2010, right? So it's important one. And here see the comparisons of technical availabilities and real availabilities and their capacity factors. So here it is also the old data. So I'm going to take as a 2000 to 2004 only. So by taking these average, I'm getting the average technical availability, which is 98.26%. And for average real availability, I'm going to take is 83.06%. And for average capacity factor, it comes around 26.61%. So the technical availability will be getting a higher percent, and your available, sorry, average capacity factor will getting a low percent, which is a 26.61%, right? And here the percentage distributions of the stoppage. So the stoppage while occur due to the emergency purpose, we are going to stop the operations of the wind frame. So what are the causes to be occurred the grid failures? So due to the substation maintenance, here I'm going to take the data. It is 12 times per year. So per year 12 times they are going to take as a substation maintenance. And so due to this reason, substation maintenance, I'm going to stop the operations, right? And due to the meter relay testings and breaker fault and overload, line problem, feeder tripping and power evacuation problem. So these are the causes of the grid failures while occurring year, right? So average stoppage due to the grid, which is 13%, right? So average வந்து பார்த்தீனாக்கா I'm going to stop grid from the electricity to the grid. It is comes around 13%, right? And mechanical stoppage, which is a 5.2%, electrical it is a 2.02, and the control panel stoppage, which is a less than 1%. So these are occur per year. I'm saying about a per year, right? percentage, this much amount of a percentage while occurring for a mechanical stoppage and electrical and control panel stoppage. And how to reduce this breakdown for a year, how to produce the continuous powers, and how to avoid maintenance, and how to reduce this breakdown time means for a better service, the fault may be occur in the evening, and we are going to reset the problem in the evening itself, and next working day morning, so the wind frames will be functions automatically. So by using these problems, so by using these we are going to reduce the breakdown time. And for a maintenance action, so for a quick maintenance actions, so there will be a no stoppage occur this much percentage, right? So the time for maintenance actions will be less, and for a better quality, right? If the better quality is available, so the no need for maintenance for 12 times here. Here I'm saying the substation maintenance is 12 times per year, right? So if you are going to operate a better quality, so follow in better quality means the operation maintenance time per year will be reduced from 12 to or 5 something, right? So in order to reduce the breakdown time, we are following these 4 points, right? And here the frequency of a failure. So here your x-axis will show the number of years, and your y-axis will show the number of failures. So in the year of 2008, eight number of failures will be occur. So here the previous slide, what I told, the failures due to stoppage of the grid and mechanical stoppage, electrical and control panel stoppage. So only four the major stoppage I am mentioning here. So apart from this, some more stoppage, some emergency purpose, and some emergency cases, we are going to stop the operations of the wind frame. So right here we'll see in the year of 2000, so 8 number of failures will occur, and in the year of 2001, 15, in 2002 it's 9 failure only, and 3, 12, and in 2004 17 failures will be occurred. So your total frequency of the failure is 61 over this 5 years. If I'm going to take a 5 years, how many number of failures will occur, how what is the total frequency of a failure while occurring last 5 years, means it comes around to 61, right? And this total number of failure is not a constant because of variation of the external load, right? Why? Because when we are going to provide some external load, so based on these external loads we are going to operate the wind frames as soon as possible, right? And this number of failures in the year of 2001 was more. Oh yeah, and it is a percentage in terms of due to 27% hydraulic units and 27% of the electrical and electronics unit component failures. So in the year of 2001, 15 number of failures will occur due to the hydraulic units and electrical electronics unit component failures, right? For hydraulic it's a 27%, and for a electrical and electronics unit 27%, right? And in the year of 2007 it is a 17 number of failures will occur here. So the problem for occurring the failure is same as it is a hydraulic units and electrical and electronics unit component failures, right? So it is as I told, it is a old data, so I'm taking a data as 2004 only, so better you can update your version up to this year 2020, right? And you are going to take a data from 2010 to 2020, how many number of failures will be occurred, and why these number of failures while occurring, whether it is occurred due to the hydraulic units, or whether it is occurring due to the electrical or electronic stoppage, or due to some emergency purpose, or whether it is occur from the mechanical stoppage. So mechanical stoppage means the gear failures will be occurred, and the motor will not able to run properly. So some mechanical stoppage will be occurred. So you may find out that number of failures in between the year of 2010 to 2020, how many number of failures will occur for the last 10 years. So you can take the data in the website, so it is available, right? And here the percentage distributions of the failure. Yes, as I told just now only, the gearbox, due to the gearbox and due to the brake pad and due to the hydraulic units and electrical electronics yaw mechanism, some failures will be occur, and due to the blade some percentage of a failure here occur. Here the graph will shows the different percentage distributions of the failure. So here majorly your hydraulic from the hydraulic unit 23% of the failures to be occurred, and apart and next to this your unit 23% failures to be occurred. So from the yaw mechanisms your motors and yaw drive to be connected, and as I told the previous slide, and what is the purpose for using the yaw mechanisms, and by using these yaw mechanisms 23% of a failure will occur for a last 5 years. So these percentage of distributions of failures while taking for a last overall 5 years only. Okay, right? This is not taken for a 1 year data. This is taken for a 5 years operation, 5 years data analysis data, right? And here the failure due to the mechanical components are 67% and electrical and electronics are 33%. So here it defines the mechanical which are comes under the mechanical failure means your gearbox and brake pad and your mechanisms, units, motor drives, all other things are comes under the mechanical components. So from the failure due to occur a mechanical component, it is a 67%, and for electrical and electronics component it is a 33%. So it is important. It may be asked in it may be asked later in assessment or end semester examinations. The questions may be arise. What is the major what is the failure occur due to the mechanical components and the electrical and electronic component? How much percentage of how much percent failure will occur due to the mechanical and electrical, right? It may be asked. So you just note it down, and more number of unit failures and hydraulic failures are occur, right? When compared with these mechanical components and the electrical components, apart from these two here your air unit and hydraulic units failure or occur, which is also included into the mechanical component, it comes under 67%. So apart from some other functions, the 33% of an electrical and electronics component failure to be occurred, right? And yes, these are the leading manufacturers for a wind turbine. So in India, so these are the leading manufacturers of a wind turbine. So here, Vestas, Enercon, Gamesa. So for a Gamesa, as this is a familiar one, I think from near the Pural and near the Chengalpet, Gamesa, it is a Spain country companies. So which is manufacturing for the wind turbine, and they are able to produce a 16,000 megawatt. So, right, so it's a top 10 manufacturers in a country for manufacturing of the wind turbine, right? So here from these leading manufacturers of wind turbine, so I think so many of a Germany company are there, and from the 1 and 4, 7 and 9, here out of 10 4 are from Germany, and from the Spain it is a 2, it is a Gamesa and Aguna. So it is from the Gamesa 16,000 megawatt, and Aguna it is 4,300 megawatt. So 2 Spain's and 4 Germany's, and here the India placing a 6th position for manufacturing of the wind turbine. So Suzlon, which is located in India, it's produces 6,000 megawatt, right? So I think I collected these data from the source in Google. So you just go to the updated one. I think this is data I'm collecting from the year of 2010 only. I think so. I'm not sure, right? You can go to the website and find out the leading manufacturer of the wind turbine. So now, who is the number one leading companies in the country for manufacturing of the wind turbine, and how much megawatt they are producing, right? You just note it down. It may be useful for your exams, right? Whether it may be also it may be asking for the asked for the in semester exam also, right? You just updated these one, right? Yes, it is the same. The top leading manufacturers in India, and what type of model they are using, and what type of a drive they are using. So most of them are using a gear train drive. As I told in the wind turbine parts itself, a gearbox to be present. So the how the as it I can show the slide on second, right? That's why you remembered where the gear trains will be applicable from the here, see this slide. It's a gear transmission. So from the gear transmission to obtaining to achieve the speed ratios, we are using a gear train mechanism, gear transmission system, right? Okay, so just know what type of model they are using. For example, if I'm going to take a game as a company, so how much is a percentage of the share, and what type of a model they are using, and what type of a drive train they are using, and how much the power rating for the games are, and what is the diameter of the turbine, wind turbine diameter, what it is in terms of a meter. So these are the specifications for manufacturing of these leading manufacturers given by, and you may just note it down. Yes, it is the expected output, that is a capacity factor. As I told in the previous slide, what is the capacity factor, which is nothing but energy generated per year to the number of turbines into how much so number of energy out number of hours operated per year. So there's a basic formula for calculations of the capacity factors. Here your capacity factor, the actual energy output of the for the year, as I told, how much energy generated, that is the actual energy output for the year, divided by the energy output if the machines operated. Is what is the exact total energy, actual energy, how much energy we are getting as an output for the total year, divided by, and how much energy if the machines is able to operate per year, how much energy the machines will be delivered for us, right, for the entire year. So based on these calculations, we are going to calculate a capacity factor. So most probably it comes around a 30 or 35% only. So here they have to show it is a capacity factor which is a 40%. I think a 30 to 35 which is enough for a capacity factor, right? And it is also expected output from the wind turbines. And it is a size of the wind turbine. So various size of the wind turbines will be available. So here you can see. So based on these diameters, the power generating capacities is maybe varied. So here your diameter, which is a 85 meter, it can able to produce a 2.5 megawatt. Here the from the ground to this top of the tip, it is a 279 feet. So almost if I am going to increase the diameter of the wind turbine, moreover your capacity, energy generated capacities may be increased, right? So here 120 meters, 394 from the ground to the top of the tip of the rotor, which is a 394 feet, right? It's a diameter for a wind turbine is 120 meter, and it can able to produce a 5 megawatt, right? So you just take take down the notes, right? Yes. Yes, I think yes, you just note down the problem at the Mupandal. There are about 15 machines of 400 kilowatt capacity is installed in the year of 2000, and the downtime due to the machine failure, grid failures, and low winds are 67 hours, 117 hours, and 133 hours respectively. So electricity generated for the year, which is 15132,716 units. Yeah, it's I think three. It's a 15 megawatt units, right? So find out the technical availability, real availability, and the capacity factor. So you may know the formula how to find out the technical availabilities, and how to find out the real availabilities, and how to find the capacity factor, right? The capacity factor, how to calculate, which is nothing but your energy generated per year to the number of turbines into the number of energy operated per year. So by using these formula, you can find out the three: technical availability, real availability, and capacity factor, right?
You know, we can stop it here. Online.
அவ்வளவுதான் sir. End ஆயிடுச்சு. This one is the last slide. So you may also take down this problem also. Okay. So from these problems, our third unit will be completed, right? You just note down these two problems.
Okay. Thank you.
Okay.
பசங்களுக்கு வேணா ஸ்லைட்ல அனுப்பிச்சு விட்ருமா.
நான் ஸ்லைட் ஷேர் பண்ணிடுறேன் சார்.
இவங்க வந்து பிஹெச்டி பண்றாங்க, கோர்ஸ் ஒர்க்.
தெரியும் சார்.
வெளியே வரணும்ல.
ஆமாம் சார், அவங்களுக்கு சொல்லிடுங்க. ஸ்லைட்ஸ் நான் ஷேர் பண்ணிடுறேன்.
ஓகே. We share the slides and then you can prepare for your test. Okay. Yeah.